All right, good morning, everyone. We're going to be looking at two descreening algorithms today. So first off, what is halftoning? Well, if you look on the left, you have an image that's continuous tone, so you have a continuous range of shades of gray there. But you can't represent that directly using most digital devices. Specifically, in this case, we're going to be considering printers. And so printers will actually perform a halftoning process where they will use a cluster of dots in different sizes or frequencies, so different spacing of dots to kind of reproduce those continuous tones. So when you look at that, your eyes are going to average it out somewhat to be the different shades of gray that you see on the left. But this can create a problem if you are scanning and reprinting or displaying on a monitor, for example, a halftone image. Because what will happen is when you're trying to re-halftone something that's already been halftoned, you get this aliasing effect that causes moires. And so you can see on the right a photo with a lot of moire effects in it. And on the left, if you look closely, you can actually see a little bit on his face some of the screen patterns from the printer. So there's two approaches to solving this problem. And the first one is to just simply remove the high frequencies caused by the screen pattern, and then you don't have to worry about the beading effect that you saw there when you reprint it. The second approach that's been commonly used is to change your screening technique when you're reprinting scanned documents. So you might just, instead of using the screen pattern, place the dots in a random pattern. So we're going to be focusing on the first approach here, and the benefits of that is that it also works with other types of displays. So it's not just printers, but also LCD screens. So one initial thought you might have is that if you're just trying to remove these high frequencies that are caused by the screen pattern, you might just want to low pass filter the image. And yeah, that's really easy to implement, but it blurs everything in the image. And so you get loss of corner and edge sharpness in the images, and you get blurry text. The first algorithm we're looking at is called hardware-friendly decoding, and it comes from Hideki et al. And it was designed as a low-cost hardware implementable algorithm. And so to that end, it uses integer arithmetic and operations based on bit shifts and adds. And it's based on this idea that you can perform a Gaussian filtering on an image using an iterative diffusion process, isotropic diffusion process. But Perona and Malik showed that you could actually get selective filtering on the image using an anisotropic diffusion equation that they developed. And so this uses a variation of that, and you can see the process down there at the bottom. So you get you take your output pixel just depends on your input pixel, and then this weighted sum that's weighted by that edge stopping function G there. And so basically, if you're in a smooth area of the image, it's going to blur a lot, and if you're at an edge, it's not going to blur very much. So here are the results that I have for the hardware-friendly descreening. And on the left, you see the original, and there's a lot of screen patterns visible there. And if you look at the right, there's still considerable screen patterns that you can see. But if you look closely at the left side of the tower, you can notice a little bit of smoothing there. And so we can see that it is working. And also notice that the text remains quite sharp in those pictures. And here's another one. The left is the original and the right is the descreened as well. And the text is sharp there too. The second approach is called segmentation-based descreening, and this comes from James et al. And this is a multi-step process for processing the image. So it's going to go through really 3 stages, which is segmentation, screen frequency identification, and then the actual filtering. So the first step of this is going to be segmentation, and this leverages the differences and variations of intensity between text and pictures. So in text areas of the image, you're going to have a different ratio of what he calls alpha crossings. And so if you look at the differences between 2 pixels that are next to each other in text, you're going to have, just empirically, this is empirically verifiable, but you'll have a ratio of alpha crossings in the ballpark of like 0.35 per pixel. And in image areas, you're going to have much higher, say around 0.6 or so. And so the first step that he does, or that they do here, is that you get, you calculate the density of alpha crossings in a small window. So you're going to start with like a small, 25 pixels by 25 pixel window or something. And you're going to repeatedly go across the image, copy that across the image, and count how many alpha crossings are in there versus the area of the window. And that's going to give you your alpha crossing density there. And if it's above a certain threshold, in this case, he recommends they recommend a threshold of 0.5, you're going to label that area as picture. So and then the next step is you're going to then look at all those picture points and perform a clustering operation to group those together. And then once you have that done, you know where the pictures are in your scan, and you can then put a bounding box around that, and then you can selectively filter just that area. So here's the results from my implementation, and this is just showing the segmentation part. So if you look at it, it's picking out those places with where there's a lot of gray tones. So on the left, you got like a gradient there on that ad, and then up at the top where it says spectator classified, that's actually shaded a little bit, so it's going to pick up that too. One thing to note here is that if you look at like on the top left ad there, you have the person lying on the ground, it's not going to detect that as an image, but because it's just solid black and you don't have these alpha crossings. But you really don't need to smooth that anyway because it's just a solid tone. So the next step is the screen frequency identification and removal. And that's going to be done using a fast accumulator function. And basically what the fast accumulator function is just, it's an array that gets initialized to 0, and then you're going to shift in row by row or column by column, because we're going to do this in both directions, and then add those column or row values to your array. And then at the end, what you're going to be left with is a sequence of numbers, and you're going to then take the FFT of that and compute the power spectra of both the horizontal and vertical directions. And then from that, you can identify your screen frequency, because they found that the highest peak in that power spectrum is going to be your screen frequency. And so once you have that, you just go down the line of the bounding boxes that you found, and you just do a box filter in there to just basically low pass filter that area. And so here are the results from this. You can see that it's considerably more smoothed out than the hardware-friendly approach, but what you get is a lot less sharpness in the edges, So you can see that computer starting to look kind of blurred out, and also just from inaccuracies in the bounding box calculation, you get some blurred out text as well. And here's the second picture. Again, you can see that the text got blurred out there on those numbers that are in the picture, but the picture is pretty much continuous time. And you can see that that bounding box calculation there did prevent the text on the right from getting blurred out. So the SBD results are really just that you get better smoothing of the screen patterns, but the inaccuracies in the bounding boxes can lead to some blurred text. Overall, though, I think that the SBD, when you look at it from a distance, produces better results overall in reducing the Mari effects that you might find. But the hardware-friendly option, again, is meant to be a really efficient implementation. So the segmentation base is definitely going to take a lot more computation to achieve the desired result. And I also think that there was probably a difference between the scanner that was used in the experiments for the hardware-friendly descreening and what I had access to, because I didn't have access to a scanner or the scanner that they used because everything shut down. Well, thank you for listening. That's all I got. Have a good day.